We'll continue our discussion on fiber Bragg ratings that we started last time. Last time we derived this sort of the coupling between the forward and backward waves due to this grating, right? The Bragg grating that is written into the core of the fiber using this UV light, right? So this was of some length L. So right, and then so we had a incident mode here, right, and then a backward propagating reflected mode. Right. And in this Bragg grating region, basically these two modes are coupled due to the reflection from this periodic Bragg structure, right, which had a period is capital lambda, and basically in these regions here, the refractive index was increased by an amount delta n due to this UV exposure, and this delta n was typically around 10 to the -4, that range. Right, so last time we derived, so if we write the total mode as in this coupling region as a superposition of this forward and backward modes with coefficients A and B, right? So then we found that we ended up with these coupled propagation equations between the amplitudes A of the forward propagating mode and B of the backward propagating mode. Right, so where this capital gamma here was basically the difference so again, so this forward propagating mode has some propagation constant beta 1, the backward propagating, let's say, has propagation constant beta 2, so this is beta 1 plus beta 2 minus the spatial frequency of the grating here. So capital K is 2 pi by lambda. Right, so for capital gamma equal to 0, that particular frequency or wavelength will be exactly at the Bragg condition. Okay, but in general, we are looking at wavelengths which could be slightly away from the Bragg condition. So capital gamma could be non-zero. Okay, and this coupling coefficient here, kappa, so that dependent on this refractive index change, that the amount by which the refractive index change, or more specifically the amount by which the dielectric constant change, so delta n square times this sort of overlap integral between the two mode profiles, right, in the core region, right? So this we wrote, if the modes are normalized such that they carried unit power, so right, so the modes were normalized such that this integral is 1. So that means they carry unit power, because this is the expression for the power carried by the mode. And So in this case, basically A and B, so mod A square will directly give me the power in the forward, the amount of power in the carried in the forward direction. Mod B square will give me the power carried in the backward direction. Right. So for example, let's say if we had a single mode fiber, so single mode fiber means there is only one mode, like the lowest LP01 mode, right? So which means both these are the lowest order LP01 modes. So actually psi1 is equal to psi2, right? So in that case, basically this coupling coefficient so now is just given by the confinement factor of the mode, right? So this is basically the integral of mod psi square within the core. So that's basically just the confinement factor. Right? How much power, the percentage of the power within the core region. So you can recall this was the core and cladding. Right? Because the grating is only in the core region, that's why this factor is coming in. Right? So the power which is extending into the cladding region, that doesn't contribute to the coupling. So again, recall that we could use a Gaussian approximation for the LP01 mode, right, in a step index fiber. So we can write this mode profile as okay. So this W naught was, remember, the spot size, right? Or 2W naught was the mode field diameter, which depended on the V number or the wavelength, right, for a particular fiber. So if we approximate this mode as a Gaussian, so this factor is basically a normalization factor such that this integral is 1. Right? So if you assume this Gaussian mode profile, then we can easily evaluate this integral, right? Because it's just a Gaussian function. So if we do that, so then we get right. So so we do this integral over the area in cylindrical coordinates because that's easier to do, right? So we have R, and then R going from 0 to A in the core region, and then the azimuth psi going from 0 to 2. Right, so this integral is very easy to evaluate. So basically we get okay, so we write beta as 2 pi by lambda times n effective. So we basically get that expression. Okay, and so you can simplify this a little bit more. So the delta n square, right? Basically we write as 2n times delta n. Okay, because this the change in the refractive index is very small, as we saw, right? Typically like around 10 to the minus 4 or so, or less than 10 to the minus 3. So the change in n square we can just write using the chain rule for differentiation. You can write as 2 times the absolute refractive index times the chain. And then we can also assume that this refractive index n is basically, the effective index is very close to that, because again n1 and n2 are very close to each other. For single mode fibers, like order of 10 to minus 3, n effective is somewhere in between. So basically, yeah, here basically we can just put n effective also just equal to n. So if you do that, then this coupling coefficient basically simplifies to so okay. So here we can directly see the coupling coefficient depends on the amount of index change that we get delta n, right? And then inversely proportional to the wavelength at which the Bragg condition is satisfied. And then this factor is basically giving me the confinement factor of the mode. Right? So this factor is always less than 1, the percentage of power in the core. Right? So typically for single mode fibers, for the wavelength of operation, this will be somewhere sort of between 0.5 to 1, confinement factor. Okay, so yeah, so basically you can see that if we get more index change here, then this coupling constant is higher. And also if the mode is more confined in the core, then also the coupling coefficient is higher. Okay. So yeah, let's now basically go ahead and solve these coupled equations to see how basically the powers of the forward and backward propagating modes evolve. Okay, so we've seen similar kinds of equations before, right? So basically we just go ahead and differentiate this with respect to z once more. So here b and this factor both are dependent on z, so we get two terms. Right, and now we can use, so for this we can use this equation. And then this basically a by dz, so we can get an equation only A. Right, so we again get the second order differential equation. So we had a similar equation for the directional coupler, remember, right? But there is some small differences here. The sign is different. If you go back and check, the sign was plus instead of minus. Okay, but we can go ahead and again solve this in a similar manner. So again, it's a linear differential equation of some polynomial order. So we can assume a solution like this, so e to the gamma z, right? And then we substitute, so we get a quadratic equation for gamma. So we get two solutions. Two eigenvalues. Okay, so basically we write this as some I gamma by 2. So now, so this capital gamma is that. So I recall this capital gamma was right, beta 1 is beta 2 minus k. So for example, if you're looking at single mode fiber, then these two propagation constants are the same. So right, and the Bragg condition is when this is equal to 0. So basically, we'll be looking at wavelengths which are close to the Bragg condition. So this gamma will be close to 0, some small number. Okay. So basically, this quantity will be real. Okay. So 4 kappa square, we are looking at wavelengths for which gamma is close to 0. Okay. So here this quantity is real, which we denote by small delta. So small delta is okay. So this is one change. So from for the directional coupler case, this factor was also a complex number or imaginary number. Okay, so we got some I times something, right? But here this is a real quantity. Okay, so when we look at the solution, so it will be a linear superposition of these two exponential functions. Okay, so I can write okay, so for the directional coupler case, these were also sinusoidal functions. So this was e to the I something plus e to the minus I something, but here now these are real exponentials. Okay, and b of z we can find. So a1 and a2 are constants again that we need to determine from the initial conditions, the boundary conditions. And then b you can find from this equation. Right? Okay, so we have now solutions for or expressions for a and b, and a1 and a2 are some are two unknown constants which we can determine from the boundary conditions for a and b. Right. So typically, what are the boundary conditions? So right. So we have an input wave coming in from here. So basically, a at 0 will be some input amplitude here, which depends on the power that we launch. And basically, the reflected wave just gets generated due to reflections from this Bragg structure, right? So basically, from here, right? So there is no wave launched from the other side, which is backward propagating, right? That just gets generated due to here. So if you look at this backward propagating amplitude at z equal to L, that should be 0, right? Because there is no wave coming from here. So these are the two boundary conditions that we can use to determine A1 and A2. Okay, so yeah, we can just put z equal to 0 here and then equate that to some input amplitude A in, and then for here we put z equal to L and equate to 0. So if we solve those equations, we can get expressions for so check for yourself at home that you get these expressions. So that's for A. Okay, so we finally end up with these expressions for the forward and backward propagating amplitudes. So the solutions are in terms of hyperbolic functions, right? Again, because these were real quantities, right? So recall hyperbolic functions are defined like this. So cosine hyperbolic of x is that, right? And so they're defined in terms of real exponential functions. Okay, so the solutions are in terms of these hyperbolic functions. Okay, so now basically we have the complete solution. Okay, so of course, one thing we are interested in is basically how much of the incident power is back reflected here, right? So if you define a reflection coefficient as, so the amplitude of the backward, so power in the backward propagating wave here at z equal to 0, so the reflected back power from the grating divided by the incident input power. Okay, so yeah, we just put z equal to 0 in these expressions and take mod square of them. So we get that expression for the reflection coefficient. Okay, so of course it depends on this delta, which is how far you are away from the Bragg condition, right? So at the Bragg condition, gamma is 0 and delta is equal to kappa. And as you go away from the Bragg condition, then gamma increases and the value of delta goes down. Okay, so we can look at the phase matching condition, which is the Bragg condition. So that is basically gamma equal to 0. So this happens at, remember, the Bragg wavelength. So at when the wavelength of the incident field satisfies this condition. Okay, so for this again, so delta is basically kappa. Okay, so here basically you put delta equal to kappa and gamma equal to 0. And we get the reflection coefficient to be, so we'll end up with a sine hyperbolic square here and cosine hyperbolic square here. This factor goes away. So sine over cosine, so we get a tan hyperbolic. Okay, so right at the Bragg wavelength, where that's basically where we get the maximum reflection. That maximum reflection coefficient is given by tan hyperbolic square of this quantity kappa times that. Okay, so tan hyperbolic. Again, so that's fine like this, right? So actually, tan hyperbolic x, you can see goes between it goes between -1 and 1. Okay, so if you plot tan hyperbolic, it actually looks something like this. It goes between -1 and 1. So here we have tan hyperbolic square, right? So that goes between 0 and 1. So this argument again is positive. So we are only looking at positive values, right? So tan hyperbolic square will basically square of this will also again go from 0 between 0 and 1. Right, so if I plot the reflection coefficient versus this quantity kappa times L, so the coupling coefficient times the length of the grating. So basically the reflection coefficient increases with, for example, the length of the grating for a given coupling coefficient. And to get to idea of some values here. So of course it asymptotically approaches 1, so 100% reflection for increasing values of kappa L. So just to give some perspective, so for kappa L equal to 3, this is about 99%. Okay, so if you put this argument equal to 3 in the tan hyperbolic square, you will see that comes out to about 0.99. Okay, so depending on this kappa, which depends on basically this delta n, right? How much index change, and then how long the grating is, we can design an FBG to give us some whatever particular amount of reflection that we want. So now if you look at this, how these amplitudes are evolving within the coupling region here. Okay, so we send in some A from here, right? So this is A in. So in the coupling region, this is Z equal to 0, and this is Z equal to L. So basically, in the coupling region, what happens is the forward wave scatters back into the backward wave. So the power in the forward wave keeps dropping. Right? So the backward wave again starts from 0. Right? So that was the condition here because we are not sending any wave from this side. So it starts from 0 at Z equal to L and then it builds up. Okay, and then finally at the input of the grating, it has appreciable power, and there's a appreciable reflection back. Okay. So if you look at this difference, so actually what I'm plotting is mod of the sort of power in the forward and backward propagating. Okay, so if you look at this difference, right? So if you calculate what is the difference in the powers of the forward and propagating backward propagating waves from here, you will see that this actually comes out to be a constant. Okay, so this is independent of Z. So basically this difference remains the same. Across the wave. So the forward propagating wave is decaying, the backward propagating wave is building up. Okay, so that's at the Bragg condition. So when delta is equal to kappa or this capital gamma is 0, right at the Bragg condition, right, this is the case. So we can also look at how the reflection coefficient varies as we change the wavelength from the Bragg condition, right? So then this capital gamma is non-zero, right? So we can plot how the reflection coefficient changes as we change the wavelength around the Bragg wavelength. So basically we are plotting this expression here, reflection coefficient versus, so the x-axis is, so you can see the relevant quantity here is so the how big this gamma over 2 is compared to kappa. So we plot this as a function of gamma over 2 kappa. Right, so this capital gamma can be positive or negative. So basically it's 0 at this Bragg wavelength. So now if we increase wavelength, then we go on one side. If we decrease wavelength, then we go on the other side. Or the opposite basically, because recall, so this gamma depends on beta, right? So it's basically 2 beta minus kappa, and beta is basically 1 over wavelength, right? So when we decrease wavelength, beta increases and gamma increases. So this is decreasing wavelength and this is increasing wavelength. Okay, so basically we get different curves for different values of this kappa L. So for example, for Okay, so this is for kappa L equal to 3. Right, so we saw already, so for kappa L equal to 3, at the Bragg condition, gamma, capital gamma equal to 0, the reflection coefficient is about 0.99. Okay, and then as we go away, the reflection coefficient drops, right, because we have this extra term here in the denominator, so the reflection coefficient starts dropping. Okay, and then after some point, we get this oscillatory sort of behavior, right? So that at first might seem puzzling because we have only hyperbolic functions here, right? So hyperbolic functions, as you know, are monotonic functions, right? So why do we get this oscillatory behavior? Is basically what happens is, so this delta, right? So you can see that when gamma out 2 kappa becomes 1, this delta becomes 0, right? And then so basically here, right, at this point, so within this range, delta is positive, right? And we have this hyperbolic functions. Beyond this, so once we go beyond plus minus 1, basically this quantity becomes, inside the square root becomes negative, right? Because now gamma by 2 is larger than kappa. So basically delta becomes imaginary. So beyond plus minus 1, delta is actually an imaginary number because this quantity inside the square root is negative. So now basically inside the argument for this sine hyperbolic, you have an imaginary number. Okay, and basically, so I mean, just from the definition you can check, right? So sine hyperbolic, remember, was e to the x minus e to the minus x by 2. So now if x is imaginary, if I write x as some I times y, then you can see that it will become e to the iy minus e to the minus iy, which is like a sine, right? So sine hyperbolic of I times x is basically just that. Right, so what happens is basically beyond plus minus 1, this hyperbolic function changes to a normal sinusoidal function. Right, and then basically now, once you have sinusoidal function, then it becomes oscillator. So I hope that's clear. So now, for example, if I look at a lower value of kappa L, so you can from here see that so the reflection coefficient will be smaller, right? So for example, if I look at kappa L equal to 1, the peak reflection coefficient is about 60%. But the bandwidth is larger. Okay, so this dotted line here is for kappa L equal to 1. The peak reflection coefficient is smaller, right? So it's about 60%, between 50 and 60%. But you can see that it falls off slower. Okay, so the bandwidth is larger for in this case. Okay, so it's basically like some gain bandwidth thing which you see in a lot of places. So if you have higher gain, in this case higher reflection coefficient, then the bandwidth is smaller. Okay, so we can estimate what is the bandwidth here by calculating basically at what points this goes down to 0. Okay, so we can define the bandwidth as basically the range of wavelengths here, right, between which basically the reflection coefficient is high. So we can calculate where this goes to 0. on both sides and then say, okay, this is the bandwidth of the central lobe. Right, so you can do that. So, right, basically you have this expression for the reflection coefficient. So again, it goes down to 0 when this sign, so the argument here is like pi, plus minus pi, right? So it will go to a value 0 beyond this gamma to kappa equal to 1. So now this hyperbolic function has become a sign already, right? So this quantity inside is negative. But when basically that quantity, the magnitude becomes pi, then this function, so here this will become sine, and then when that argument becomes pi, or plus minus pi, plus or minus pi, then the reflection coefficient becomes 0. Okay, so you can find out where that happens for which values of, right, you can easily do that using this relation and equate it to pi. So basically, and then use the relation basically that gamma is 2 beta minus this capital K. Right, so basically the procedure is, so from here you can find out for which values of gamma this becomes 0, the R becomes 0. So you get 2 values of gamma there, and then use basically gamma is 2 beta minus kappa, or basically this is 2 pi over lambda times n effective minus 2 pi over capital lambda. Right, so you get a gamma plus here and a gamma minus here. So you get a lambda plus and a lambda minus, and then you can define the bandwidth basically as the difference between these two wavelengths. Okay, so basically you can check. Okay, so the bandwidth in wavelength units you get like, so where lambda b is the Bragg wavelength. So lambda b is where this condition is satisfied, capital gamma is 0. Okay, so you can see that the bandwidth scales with this value kappa times L. Okay, so that's the bandwidth calculated from where the reflection coefficient becomes 0. So, or like basically the width of the central lobe. Yes. There is simpler approximate expression for the bandwidth which is used often. Okay, that sort of gives you more like a full width half max bandwidth. So basically, the range where the reflection coefficient drops to sort of half the maximum value. So, okay. So it's basically the Bragg wavelength times the ratio of the grating period to the length of the grating. Okay. So this expression for the bandwidth typically will give you a lower value than this, right? Because this sort of approximates or estimates the full width at half max, whereas this one estimates where it goes down to 0. Okay, from here, sort of you can see that if you have a longer grating, then the bandwidth is smaller. Again here, because of the L coming in the denominator. Okay, so if you plot this reflection coefficient in terms of wavelength, right, which is what ultimately sort of we are interested in, right, for practical applications, then basically we'll get some similar curve like this, but just in terms of wavelength, right? Because these quantities depend on wavelength, as you've seen. Right, so let's say, for example, we design an FBG for 1550 nanometer wavelength. So the Bragg wavelength is 1550 nanometer, the telecom wavelength. Okay, so then roughly the period required would be that, right? And so N effective, we can just say, okay, it's the silica glass factor index 1.45. So this comes out to be about 530 nanometers. Okay. So as we already saw that the period of the grating typically is much smaller than the wavelength. Okay, so typical delta N values that we can get with this UV exposure is about, so this is, let's say, 4 times 10 to the minus 4. Okay, so then this coupling coefficient we call, so it went something like this. Right. So if you put these numbers here, so this confinement factor was between 0.5 and 1. So for now, let's say this is close to 1. So this number comes out to be about 0.8 per millimeter for these values. So you can also you can explicitly calculate this, right? So we know, for example, we have approximate empirical expressions for W0 over A in terms of the V number, right? So for a given fiber dimensions for this wavelength, we can calculate what this also would be. So typically it's between 0.5 and 1. Okay, so if you look at, so we now have a value for kappa. So if we calculate the peak reflectivity that we get at this wavelength, so let's assume if you take a grating length about 2 millimeters, then this comes out to be about 0.85. Okay, and then if you calculate the bandwidth from this expression, that comes out to be about 0.8 nanometer. Or if you calculate using this expression, it comes out to be about 0.4 nanometer. So this is the width at half max, and this is the width of the central lobe. Yeah, so this gives you some idea of some numbers, right? So typically, so you can get like reflection at particular wavelengths, right? So you can see delta lambda is quite small here. So basically, if you plot reflected versus wavelength, basically you get a sharp peak, right? So this and lambda p, and then this delta lambda is typically very small. Right. Alternatively, if we look at the transmitted power here, that will be 1 minus reflection, right? So that will look something like this. So you can see in the transmission port, it looks like a notch filter. So it rejects some particular small band of wavelengths and transmits everything else. In the reflection port, it's like a narrow band pass filter. So it only reflects particular wavelengths. Right, so basically you can design these fiber Bragg gratings for any wavelength you want with some particular bandwidth and peak reflectivity, right? By controlling this delta n and the period. So you can, for example, look at another example. So let's say now I want a FBG at 50 nanometer. So of course the grating period is decided by the wavelength, so that will be the grating period. But now let's say I want a peak reflectivity of almost 100%. So let's say I want this to be 99%, right? So from again, so this is equal to tan hyperbolic square kappa L, right? So we can write tan hyperbolic as e to the x plus minus e to the minus x divided by e to the x plus e to the minus x. So we can basically get what kappa L should be like that. Okay, so this comes out to be about 3, as we already saw in the plot, right? For 99%, kappa L needs to be about 3. So so basically we want peak reflectivity 99%, and let's say we want a bandwidth of 1 nanometer. Okay, so those are the design parameters. So I want a FBG at 50 nanometer with peak reflectivity 99% and bandwidth 1 nanometer. So from the peak reflectivity, we get what value of kappa L we need, and then from the bandwidth, right? So again, if you use this expression for the bandwidth, so we already know what kappa L is, right? So from here we can get what L we need. So from here basically we get the L is about 2.3 millimeter. Okay. So again, so kappa L is 3. So from here we get that the coupling coefficient needs to be about 1.3 per millimeter. And again, because this coupling coefficient basically just depended on the refractive index change. So typically, like for standard single mode fiber at 1.55, this confinement factor, let's say, is about 0.75. Okay, so basically from here we can calculate what delta n needs to be. Right, so to basically make a fiber grating, what all do we need? We need what period we want, what length, total length, and what it should be this delta n, which depends on the power of the UV, right? So basically these are the three parameters that we need to make a FBG, right? Delta n, period capital lambda, and total length. So we found what length we need, what period we need, and then what index change we need to calculate from here. So that comes out to be 8 times 10 to the minus 4. Okay, so this is how we sort of design and then make FBGs for particular applications. Okay, so these FBGs, you can see they work as like optical filters, right? So they are used in a lot of places, particularly, for example, as add-drop filters in optical communication systems, where we are using wavelength division multiplexing. So we have multiple wavelengths traveling through our fibers, and for example, we want to take some particular wavelengths out of those and send them to some other towards some other direction, right? So we need to pick out some wavelengths or maybe add some wavelengths into the channel. Okay, so you can see that this is picking out particular wavelengths, right? So they can be used as add drop filters to add and remove wavelengths. So for example, how that's done is so let's say you have some fiber here and you have multiple wavelength channels traveling through this fiber, right? And now basically I want to take one of these wavelengths, right, and then send it through another fiber going somewhere else, right? So I need to take some part of the data and route it to some other portion. So typically how that's done is, so you use a device which is known as circulator. Okay, and then you have this fiber Bragg rating here. So let's say I want to pick out lambda 1. So then basically I have a FBG which reflects wavelength lambda 1. So basically from here lambda 1 is reflected back and all the other wavelengths are transmitted. Okay, and this circulator device basically it's like a non-reciprocal device. So it works on the concept of optical isolation. So you might have learned about isolators, optical isolators from your basic optics course, right? So they allow light to travel in one direction but not the opposite direction, right? So for example, typically that is done using magnetic fields and some magnetic material which rotates the polarization, right? So you can build these isolators which only let light pass one way. So based on that, so this is like a 3-port device based on this optical isolation. So it only allows light to travel in one direction. Okay, so if we have light from coming here, it will only go here. But if we have light coming here in the backward direction, it goes here. It doesn't go back. It goes to the 3rd port. So basically, light travels like in this clockwise direction in the circulator. So if you send from here, it will go back here. Okay, so basically what this circulator does is basically it isolates the reflection. So the reflection coming goes to the other port. So now lambda 1 now is going to. Right, so again down the line we could have now other FBGs, so to pick out other wavelengths, right, with again circulators. So we could pick out wavelengths like this, and we could also add wavelengths, right? So we could do the reverse and add wavelengths into the channel. Okay, so they are used as these add drop filters. And so FBGs are basically like mirrors at particular wavelengths, right? And you know that, for example, in lasers, right, we build these optical cavities and where gain is going on within the cavity, right? And particular wavelengths built up within the cavity, right? Which ultimately lays. So you can make fiber lasers using these FBGs. So for example, let's say you take a piece of fiber, right? In the middle, you dope it with erbium. So here you have erbium doped fiber, right? So this is like gain medium you already studied, right? So, so in this region, let's say you have some coupler here. It's 980, 350 couplers, right? So you send your 980 pump. And then what you do is, so from where your signal is coming, that needs to be amplified. Or in this case, you're building a laser, so actually there's no input signal, right? If you use it as an amplifier, as we already studied, we have a weak signal incoming that we amplify. But if you want to build a laser, basically what we do is build FBGs, so you can build these fiber Bragg gratings into the same fiber on both sides, okay? And you can design this to operate at whatever wavelength that you want to laser at. So for example, if you want 1550, then you can have these reflecting at 1550. So you can see basically what happens is that, so you pump here, you get some spontaneous emission over the erbium bandwidth, and then only the wavelengths which are reflected by the FBG, they circulate within the cavity, right? And then they experience more gain. And at some point, when the gain becomes equal to the round trip loss, then basically you start getting laser, right? So you get a laser output at whatever wavelength you design these FBGs for. So you can build compact all fiber lasers like this, right, at particular wavelengths. So you can build it for any wavelengths within the erbium bandwidth, which we saw is quite broad, right, from almost 1.5 to 1.6 micron. So depending on where you design these FBGs for, you can get lasers at those wavelengths. Okay, and they're also used for other things like sensors and a lot of things.